All right, in this first lesson, we're going to take a look at a couple of the first concepts associated with heat, namely, what's our model for heat? What actually do we mean by heat? And then we'll move into another category called specific heat. And that's really important as we start our first problem solving. So let's go ahead and take a quick look. I'll make this a little bit bigger so it's easier to follow along. And when we start off talking about heat, we'll refer to the kinetic theory of heat, which really relies on classical mechanics. We assume that we have sort of that atoms are more like billiard balls, that they bounce around and have energy sharing collisions and they conserve momentum. And because we assume that energy is conserved in those collisions, that characterizes them as being elastic. So then when we connect this internal kinetic energy to macroscopic things that we can measure, that is temperature. So temperature is a macroscopic manifestation of what's happening on the molecular level. We can get a sense about this by taking a look at a quick simulation. So I'm going to stop this slideshow and then share a different part of my screen, which is gas properties. So you can find this. PHET is for physics, educational technology, and a lot of really wonderful simulations are on this website. You've probably heard of it before. Now let's take a look. Excuse me, here's our container. We've got a fixed system, and of course that's a big idea in science when we try and reduce things to their simplest forms. We can control the volume of this container, the system. We can actually control whether the system is open or closed, and we can add heat or remove heat. We can measure temperature, that macroscopic variable, and pressure is another macroscopic variable. We'll start off by injecting some particles at 300 degrees Kelvin, and they all start off with the same speed, but it doesn't take very long before they start acquiring a number of different speeds. So some are going really slow, but there's a collision and it picks up kinetic energy and momentum. If I interject some lighter particles, then we can see that they don't have the same typical speed. So their average speed might be quite a bit higher. And that's because they have lower mass. So for everything to be at the same temperature, that means the same average kinetic energy. If the lighter particles are going to have the same average kinetic energy, that means they have to be moving faster. So in this distribution of speeds, this is not the typical error curve that we're used to seeing, like when grades, for example, are graded on a curve. This distribution is asymmetric because it involves zero. However, as temperature increases, the shape of the curve will start to decrease because as we get to higher temperatures, the effect of zero is not as much anymore. So when we talk about heat and energy can be synonymous, but specifically, heat is the flow of energy from one place to another. SI units, the joule. An alternative unit is the calorie. We're familiar with the definition of calorie. And then a rather amusing definition for a British thermal unit, which we still use in heating and cooling, the BTU, is the amount of heat necessary to raise 1 pound of water by 1 degree Fahrenheit. And I don't know why that makes me chuckle, but I'm just picturing a pound of water. Anyway, heat is a transfer that's caused by a temperature difference. And so this is just an interesting little experiment that you can do, is that you can put your palms together and see if that feels warm or not. And the interesting part of why it feels warm is why your palms feel warm is even though there's not a lot of heat transfer happening between your hands because they're at the same temperature. What you've done is you've cut down on the loss of heat through the surface of your skin. And that's why a blanket makes you feel warm, is because when you cover up your blanket, you're cutting down on the loss of energy, the loss of your bodily energy. So different systems are going to store energy in different ways. If now, instead of thinking about just billiard balls floating around, we can think about other different shapes, like here's a diatomic molecule, and it can move in different ways. So not only can it translate along X, Y, and Z axes, it can also rotate, can spin. We might also have a place where this bond is a little squishy and they can vibrate with respect to each other. So there are different modes for being able to store energy. So different systems can store energy in different ways, and each one of these ways is called a degree of freedom. Now, when we add energy to a system, if it has lots of ways of storing energy, then the temperature is not going to increase as fast. This leads us to the concept that depending on the material, the proportion of temperature increase to how much heat is added will be different. Specific heat measures that for different substances, and we're going to focus on SI units, which are joules per kilogram per degree C. So when we add heat, Q is for heat, then the amount of temperature increase will depend on how much stuff we have, that's mass, and then what kind of stuff we have, and that's where specific heat comes into play. The combination of these two together, M times C, is the total heat capacity. You can see that metals are not very good at holding on to their heat, except for aluminum. Aluminum's not too bad. But then when we take a look at liquids, liquids are very good at retaining their heat. They have lots of different ways of storing energy, in particular, the intermolecular forces. And water, of course, you can see is a champ on this list. All right, so now with these variables, we ought to be able to specifically find out when temperature increases, how much heat is going to be required for that temperature increase. All right, well, let's pause this, and the next lesson is going to take a look at some simple problem solving.